Angular momentum. The angular momentum of a rigid body rotating about a fixed axis is the product of its moment of inertia I and its angular velocity omega. We call angular momentum capital L. Remember, angular velocity is in radians per second. Previously, we saw that the linear momentum of an object is equal to its mass times its velocity. We see a pattern here since moment of inertia is the rotational analog to mass, and angular velocity is the rotational analog to linear velocity. We also talked previously about the conservation of linear momentum. The total linear momentum of a system is conserved, meaning that total final linear momentum is equal to total initial linear momentum, when the sum of the average external forces acting on the system is equal to 0. Similarly, the angular momentum of a system is conserved, meaning that total final angular momentum equals total initial angular momentum if the net average external torque acting on the system is equal to 0. Let's look at an example problem. On my ice skates, I start out spinning with my arms outstretched and then pull them in, as shown. With my arms outstretched, the distance from fingertip to fingertip is 2.2 meters, and I'm spinning at 1 revolution per second. When I pull my arms in, my diameter of rotation becomes 0.52 meters. What is my angular speed after I pull my arms in? Ignore friction and air resistance. Now, what are we given? The initial distance from fingertip to fingertip is 2.2 meters. We'll call this my initial diameter of rotation, d initial. And my final diameter of rotation is 0.52 meters. My initial angular speed when my arms are outstretched is 1 revolution per second. Let's go ahead and convert that into SI units of radians per second. 1 revolution is 1 circle, which has 2 pi radians. So we'll multiply 1 revolution per second by 2 pi radians per revolution to get 2 pi radians per second. Now we're looking for my final angular speed after I've pulled my arms in, so we need an equation. The gravitational force on me and the normal force from the floor on me balance each other out, and we can ignore friction and air resistance. So that means that the net average external torque is equal to 0, and total final angular momentum is equal to total initial angular momentum. Angular momentum is equal to I times omega, so we'll substitute that in. Now we'll solve for final angular speed, since that's what we're looking for. We have a value for omega initial, but what about for I initial and I final? We'll use I equals mr squared as an approximation. So we'll substitute that in. Now we can cancel mass out, which gives us this expression. The initial radius is just half the initial diameter, and the final radius is half the final diameter, so we'll write those out over by our given values. Now we can just plug in our given values into our expression, and using our calculator to solve, we get a value of 112 radians per second for my final angular speed.